Hey friends, my name is C and you're watching MakesItEasy, and welcome to a new video for A level for the lessons today. We have 2.4 for Loci in the Argand diagram for the rules and examples video. And we'll first look into circles and locus, but before we get into it, don't forget to leave a like, subscribe, and ring the notification bell so you don't miss out on any future video. And we're now into circles and locus. So the definition of a circle is, for example, a set of points equidistant from a fixed center, where equidistant basically means the same distance. So the equation of a circle in the factor form is x minus h squared plus, like brackets, y minus k squared equals r squared, where the circle has center hk and radius r. And the equation of a circle in expanded form is x squared plus y squared plus ax plus by plus c equals 0. And we can get from the expanded form to the factor form by completing the square. And we have a diagram on the right here. On the right, it shows the modulus of z equals 3, where it basically means the modulus of the complex number has to be 3. This means that any point that has a distance of 3 from the origin satisfies the equation, so it forms a circle of radius 3. So what it means is that basically we know that z, the most basic complex number, is in the form of z equals x plus iy. And if you were to let z as just like the origin, like 0, 0, we know that the origin is here, and any point that has a distance of 3 away from the origin will form a circle. For example, it will form, this is 3, 3, 3, 3, 3, because they are all the radius. Therefore, it forms a circle, and we call this a loci. And because a loci or a locus is a set of all points, usually from forming a curve or surface, satisfying some condition, and in this case, it happens to be the distance is equal to 3. So moving on, we have loci and the different forms. So we look into the loci in the form of the modulus of z2 minus z1. So for two complex numbers, for example, z1 equals x1 plus iy1 and z2 equals x2 plus iy2, the modulus of z2 minus z1 represents the distance between z1 and z2 on an Argand diagram. So for example, we have z1 here, this point is z1, and z2 is here. And the distance from z1 to z2, which is this right here, is z2 minus z1, because it's basically like vectors where you go from here to the origin and back to here. And this one right here is z2, and this going backwards is minus z1, so it would be z2 minus z1. So the second form, which is more common in further maths, is loci in the form of the modulus of z minus z1 equals r. So for the complex number z1 equals x1 plus iy1, the locus of point z on an Argand diagram such that the modulus of z minus z1 equals r, or we can basically just rewrite z1 as x1 plus iy1 as shown here equals r. This means that the circle has a center x1, y1 and the radius of r. So here's just a little simple proof for the center. So we know that this can be turned into Cartesian form, right? Like we can just reverse the whole modulus. So z minus z1 equals r, like the modulus. We can substitute z by x plus iy because it's a generic point on the whole plane or on the diagram. So z equals x plus i1 minus z1. We're given it as the complex number x1 plus iy1. So z1 equals x1 plus iy1, right? And we can basically just group the common terms. So I just basically expanded negative, like here, like so, and then group x minus x1 right here, because there are real components, and for the imaginary components, it's basically just y minus y1, and there should be an I here. Sorry, I, like so, right? So now you can basically just reverse the whole modulus. So the way to do this is that we square individual components, and square root it. So for example, here we have the root of x minus x1 squared plus y minus y1 squared equals r, right? And the way to reverse this is that we can square both sides to get x minus x1 squared plus y minus y1 squared equals r squared. So as you can see from here, this basically represents the equation of a circle we saw just now, where the circle has center x1, y1, as shown here, and radius r, as shown here. So here's an example. So we have a circle and the locus of point, and here we have z minus z1 right here, and z. So every point z on the circumference of the circle is a distance of r, or the radius, from the center of the circle. And lastly, we'll look into the loci of the form the modulus of z minus z1 equals the modulus of z minus z2. So for two complex numbers z1 equals x1 plus iy1 and z2 equals x2 plus iy2, the locus of points z on an Argand diagram such that this right here is a perpendicular bisector of the line segment joining z1 and z2. So for example, here we have z1 right here and z2. This is the locus, where it's a straight line but not a circle, because it's a different case. This is the locus because it's basically a perpendicular bisector of the 2 points. That means that every point on this line is equidistant to both z1 and z2. For example, here, this distance is the same as this distance. Let's say here, this distance is the same as this distance, which is pretty cool. And here we have some examples for loci. Given that the locus of points is represented by the modulus of z minus 5 minus 3i equals 3, sketch the locus of points. So we know that the locus is z minus 5 minus 3i equals 3. What we can do is that we can basically just factorize a minus first by doing this. We can just do z minus 5 plus 3i, right? Because if you were to expand it, it would be minus 5 minus 3i as shown on top here. So this equals 3. So from here we can deduce that the center of a circle, the center, C, equals 5, 3. And the radius equals 3, right? Therefore we can plot it quite easily. We know that, let me just draw this right here. The real axis and the imaginary axis right here. I am imaginary. So we can plot 5 at around here and 3 around here. So 3 and 5. We know the center is 5, 3, that means it's here. And we know that the radius is 3, right? That means the circle must have a radius of 3. That means it must touch this point right here. Because from here to here is 3. Oops, is 3, right? 3 units. And it can't, and the circle can't touch the imaginary axis because from this point right here to the imaginary axis is 5 units, and it has only a radius of 3. That means it will only reach 2 right here, because 2 to 5 is 3 units. Therefore, it will reach around here. Therefore, we can basically draw a circle which looks like this. So it's a bit not proportional. So I'm just zoom down, and that basically looks right. And the radius isn't very accurate, so I'll just label some points. So this will be 3. Oops. This will be 3. And let's say this will be 3 as well. And find the Cartesian equation of this locus. So as seen just now, we can basically just set z as x plus iy. So we can just set x plus iy minus 5 minus 3i equals 3. We can collect like terms like the real part and imaginary part, so x minus 5 plus y minus 3i equals 3. We can square individual terms and square root the whole thing. So it will be the square root of square root of x minus 5 squared plus y minus 3 squared. Holding square root, holding square root equals 3. Therefore, you can basically just reverse the whole thing by just squaring both sides, and therefore this gets us x minus 5 squared plus y minus 3 squared equals 9, like so. And here we have another question. Find the Cartesian equation of the locus of z if the modulus of z minus 3 equals the modulus of z plus 1, and sketch the locus of z on an Argand diagram. So we can just first substitute z by x plus iy. So it will be x plus iy minus 3 equals x plus iy as well, plus let me just rewrite this, x plus iy plus I. Collect like terms to get x minus 3 plus iy equals x only plus y plus 1i. So we can square root both sides, square both sides to get rid of the modulus symbol on both sides and square individual terms. Therefore, this gets us root of x minus 3 squared plus y squared equals the root of x squared plus y plus 1 squared, like so. And we can get rid of the square root symbol on both sides and expand the brackets. This gets us x plus x minus 3 squared is x squared minus 6x plus 9 plus y squared equals x squared plus y plus 1 squared is y squared plus 2y plus 1. So we basically have an equation where you just have to simplify everything. So we can cancel the x squares and y squares on both sides, right? This left us with minus 6x plus 9 equals 2y plus 1. Therefore, we can just we can rearrange it to get into the form of y equals mx plus c. So it will basically be minus 6x plus 8 equals 2y. Therefore, y equals, let me just use a new color. So therefore, y equals minus 3x plus 4. It's a bit of a jump here, but what I did was that I minus 1 on both sides. So it gets minus 6x plus 8 equals 2y, and divide everything by 2. And sketch the locus of z. So it's basically the line y equals minus 3x plus 4, right? So let me just draw an axis here. So the imaginary axis, imaginary, and the real axis. So you just basically have to plot y equals minus 3x plus 4. So this the y intercept will be 4, which is basically on the imaginary axis, 4. And when x equals 0, y will be 4, right? And if y equals 0, x would be 4 over 3, around here, right? So therefore this would be the line. Because if we were to substitute 0 equals minus 3x plus 4, we can solve x to be 4 over 3. Therefore, this will be the line right here. So this will be the locus of z, like so. And here we have minimizing and maximizing arguments. So here's a recap. The argument of a complex number is the angle its corresponding vector makes with the positive real axis. So here we have two diagrams and some notes. The minimum value of arc z, the argument of z, will be the angle from the positive real axis, this one right here, the real axis, to the closest point on the locus or the circle. And the maximum value of arc z will be the angle from the positive real axis to the furthest point on the locus or the circle in order to generate a larger angle. So here we have two examples right here. We have two diagrams. So we can see that one is where it touches the real axis and one it doesn't. So for the one it touches the real axis, so this angle right here will be the minimum argument. So basically alpha equals the minimum argument. So, and 2 alpha is basically the whole angle right here is basically the maximum argument. Because as you can see here, the argument is basically from the real axis to the closest point. So imagine you just make a line from the origin to the center of the circle. And the angle right here will be the minimum. And if you were to draw another line from the origin to where it touches, which is basically the tangent to the circle, where here it forms a 90 degree, this angle right here would be a maximum. So for the one that doesn't touch the real axis, we can basically draw two lines here, a few lines here. So we can draw this line here where it basically touches the circle, where this forms a right angle, which basically means that this is a tangent and this is also a tangent. The minimum argument will be the angle this right here plus alpha, right? So we just have to make sure we have to find this angle right here by doing some trick, because we can find this angle and this, we can find this length and this length to find the angle. And basically theta plus alpha equals the minimum, and theta plus 2 alpha equals the maximum, like so. And just have to make sure that these are all right angles. They're like right angles, right angles, right angles. It's really important. And lastly, we have minimizing and maximizing modulus. So here's a recap. The modulus or absolute value of a complex number is the magnitude of its corresponding value. So the minimum value of the modulus of z will be the distance from the origin to the center of the locus or the circle, or like the modulus of z, and subtract the radius of the circle. It's quite important. And the maximum value of the modulus of z will be the distance from the origin to the center of the locus or the circle, or the modulus of z, and add the radius of the circle. So what I mean is that we have a diagram right here. We have this line that connects from the origin to the center of the circle. The minimum value of the modulus will be this thing right here, minus the radius, which means that this point right here, just this, is the minimum. And the maximum is where you have this from the center to the center of the origin to the center of the circle, plus the radius, plus this. That means the whole thing right here is the maximum. So that is the difference. And that's the final concept or answer. And that's it for this rules and examples video for loci in the Argand diagram. And I hope you'll find it useful and helpful. And if you did, please leave a like and subscribe and ring the notification bell so you don't miss out on any future videos. And if you have any questions regarding my channel or my YouTube or my Instagram, you can leave them down below and I'll reply to them. And check out my social media in the description, for example LinkedIn or YouTube or Instagram. And if you need any learning resources or any teaching resources, you can check out my website in the description, or you can type it out in your browser at www.makesiteasy.com. And I hope you all find it useful and helpful, and I'll see you all in the next video, which will be 2.4 for loci in the Argand diagram for the questions video, which will be fun and interesting. But until then, stay safe and happy learning.